Okay. The next speaker is Asmi Haldar, and she will be talking about dynamical freezing and emergent conservation laws in strongly driven interacting Fluke-mat.
Thank you very much. So I'd like to start with thanking all the organizers for organizing this very nice and stimulating conference and giving me the opportunity to present my work here. So I'll be talking about dynamical freezing and emergent conservation laws in strongly driven interacting Fluke matter, and this is a work which is done with in collaboration with Anirban Das, who is probably in the audience, Arnab, who is in the audience, Shagnik is also in the audience, Roderich was here last week, Frank Polman, Dibyendu is probably also in the audience, Luke and Alex. So the plan of the talk is the first part will be most of the recapitulation of the dynamical freezing phenomenology, which Arnab talked about last week. So this might be repetitive for the people who were here last week, but I'll keep it very brief, and you might also see some of the slides in common. And the next part will be the new results regarding the stability of emergent conservation laws. So to start with, the general question of thermalization, that you have a bunch of interacting degrees of freedom, you drive them periodically. So I'll only be talking about closed systems. So you drive it periodically, and then what happens to the system in the long time. So intuitive expectations are the unbounded heating, that there will be energy absorption from the drive, and there will be Fermi's golden rule type of scenarios. And there are the very the recent all the interesting steady states, which are the non-equilibrium steady states. We have heard a lot about various aspects in this conference for the past few days. So in a bit more details, just if you take a non-interacting many particle system, drive them periodically, it goes to a generalized periodic Gibbs ensemble. Now if you have many particle localized system and in presence of interaction, so and drive them periodically, you have this interesting Fluke MBL. There are stark localization, and time crystal is one of the very nice example of this regime. And of course, then there were discussions about these many particle system with interaction where there were no intrinsic localization, and in general, they are expected to go to a featureless infinite temperature-like ensemble, but there can be, of course, some very nice examples of these pre-thermal states. So all of these were very nicely covered in the pedagogical lectures that we had last 2 weeks by Roderich and Anatoli. You can just go back for very nice reviews. So just to set up the terminologies for the Fluke setup, that we have a time periodic Hamiltonian here, which is time periodic in capital T. The time evolution operator corresponding to that is the unitary U, which takes the wave function psi 0 to psi t. One can define the effective Hamiltonian, which is time independent over one period, like this, that e to the power minus I h effective t. In general, this h effective, the effective Hamiltonian, doesn't commute with any local operator. So, you observe stroboscopically, so after each time period, and the evolution due to the time dependent Hamiltonian H effective, that just gives you the wave function after time nt. So the important thing to note here that the eigenstates of the H effective, which are called the Fluke eigenstates, they play the same role as the played by the energy eigenstates in the time independent drive Hamiltonian in a quench, provided we observe only stroboscopically. So I denote mu i's as the Fluke eigenstates corresponding to the unitary over 0 to capital T. You can, which form a complete basis. So you write down any initial state psi 0 in terms of these flow eigenstates. And in the long time, the expectation value of any local operator will be given by this diagonal ensemble average, which is the flow diagonal ensemble. So, right. So now to start with the concrete example, we have a clean system. So there is no disorder and it's non-integrable, and we drive it under a strong periodic drive. So drive amplitude will be strong. So in details, the Hamiltonian is the undriven part of the Hamiltonian is there is this nearest neighbor Ising interaction, then there is this next nearest neighbor antiferromagnetic interaction, then there is also a static longitudinal field, and then there is also a transverse field which is static, and now we drive the longitudinal field with the drive amplitude hxd. So just as a first glance, that we for example start with a fully polarized state and see the evolution of that state and measure the magnetization. So if your drive amplitude is very small, then you see the that the system thermalizes very fast and the magnetization goes to 0. And if you drive it with a large drive amplitude, where here hxd is of the order 30 maybe, so then the magnetization remains close to its initial value. So the inset, in the inset, the dashed line gives you the diagonal ensemble average, and the red one is the real time. So it just keeps on fluctuating around the diagonal ensemble value. So now if you look at the diagonal ensemble average of the magnetization as a function of your drive amplitude, it shows this kind of a threshold, where in the small drive amplitude regime, everything thermalizes, and in the strong drive amplitude regime, you see there is a sharp, so it's very sharp, where you see that the system remains frozen to its initial state. So, right, and if you look at the system size dependence in the thermalizing regime, you'll see that with increasing system sizes, the system thermalizes more, and in the frozen regime, maybe if you look at this region, you see that with increasing system sizes, this trend is reversed. So with increasing system sizes, the system is more and more frozen. So the 2 point to note here is that the threshold doesn't move with the system size, and the final resolution shows that magnetization is more strongly frozen for larger L above the threshold. Now, beyond the threshold in the frozen regime, which we call the dynamically frozen regime, if you look at the diagonal ensemble average as a function of drive frequency, this kind of a peak valley structure that appears. So there are these particular points in, so this is for a fixed drive amplitude and as a function of your drive frequency. So at these points, you see a perfect freezing, and in between there are these valleys. And this also basically shows you that how the longitudinal magnetization emerges as an approximately conserved quantity under these particular drive conditions, where your drive amplitudes are integer multiples of your drive frequency. The interesting point to note here that this happens over a very broad region of omega, so it's not just the high frequency regime where we understand things a little better. So so it happens for a very large region of drive frequencies. So now to understand how well these, so this magnetization which emerges as a conserved quantity is conserved, we basically define these quantities where your X alphas are your computational basis states. So X alpha is the alpha-ith eigenstate of all the Pauli X operators, and mu alpha is the alpha-ith Floquet eigenstate. And if you so first, if you plot the magnetization of all the Floquet eigenstates, you see that there is this steps, right, kind of structures appear for the particular frequencies where the perfect freezing condition satisfies. And if you move away from the perfect freezing conditions, then this step kind of structure is a little bit smeared out. So, so we define the quantity delta, which basically gives you the measure of how well all the Floquet eigenstates Floquet eigenstate preserves the magnetization. So this is basically the expectation of magnetization in the X basis states difference and the difference of the difference between the magnetization of the Floquet eigenstates and their sum of them. So basically, I'll show you later that this delta decreases with L as at the perfect freezing points. Like for here, for example, omega 10 or 20. So, so delta gives you a measure of the violation of the emergent conservation law over the entire Floquet spectrum. So how general is this phenomena of dynamical freezing and the emergent conservation law is? So to show, but this is just to briefly state that you can take in your undriven part of your Hamiltonian, you can take all possible kind of, for example, you can take a 3-spin interaction term. You can take a long-range interaction term. You can also take a Heisenberg interaction term, and this phenomena survives, and this peak value kind of structure also survives for different kind of undriven parts of the Hamiltonian. The only thing is important that the drive amplitude is large. And how this scales with the system size. So this just for all the various models that I just mentioned, for all of them, with increasing system size, there is not much, I don't see any system size dependence. Right, so now to understand how robust this is, how much of this is a finite size effect, we do tensor network based. So we do the ITEBD kind of algorithms, which is for the infinite size system. But of course, we can do only for finite times. And now, so here I show so the blue one is for a finite size system, which is L equal to 12, and the diagonal ensemble average, which is T tends to infinity. And the red one is for an infinite size system, but of course for finite time. So, and the red one, so I just plot the final magnetization up to which I can evolve the system until and unless you blow up the dimension of, so the bond dimension of your matrix product state. And it turns out that this threshold doesn't move. So even for the finite time data of the infinite size system has the same threshold at this same drive amplitude in between, somewhere between 15, somewhere around 15. So this is again starting with the fully polarized state. And if you look at the entanglement entropy of the state as a function of time, then you see that there is almost no entanglement growth for the system for a very, very large time. And right, so this blue region is the strongly frozen region. And in the inset, I show the resonances from that I'll just briefly talk about later. Because Arnab already discussed all these in his talk, so I'll just mention that. From the perturbation theory, we can get the first order resonances, and even for the infinite size system, the resonances are isolated, and they are only the, so the location of these resonances are from are at the same point where we get it from the first order perturbation theory, and all of these points of thermalizations are can be explained from the first order resonances. So summary of the analytical results that we have is, one is the Magnus expansion, that an appropriate Magnus expansion in the time-dependent frame is consistent up to the initial two orders with the emergent conservation of the magnetization for Ising interaction of any sort in any lattice dimensions and for any two-body Heisenberg interactions or on a lattice of any dimension. And the other analytical result is the Floquet-Dyson perturbation theory, which was developed by Diptiman here, that all the physically relevant resonances that are observed in exact numerics are isolated in the parameter space and are explained completely by the first order Floquet perturbation theory. This is consistent with the fact that our divergent perturbation expansion is asymptotic to a function or convergent series with isolated singularities in the parameter space. So here you might want to have a look at the talk, the discussions after Arnab's talk, where Anatoli made a comment about these asymptotic series. So the summary is that you have an interacting system, you drive them periodically, and under the strong drive condition, it fragments the Hilbert space in these sectors of the magnetization, so that the states from the same magnetization, they are free to mix with each other, and the states from the different magnetization sectors, they are not allowed by these emergent conservation laws to mix with each other. So where HXD was the drive Hamiltonian, and MX corresponding to that, that part of the Hamiltonian emerges as a conserved quantity. So there is no hybridization between various eigen subspaces of magnetization. Now, the question is that whether everything mixes completely ergodically within this, for example, if you look in one eigenspace of this magnetization sector, whether everything mixes completely ergodically. So to understand that, what we did was to start with, we take a finite size system, for example, L equal to 12, and we start with all possible kind of computational basis states and evolve them with this under this strong drive, and look at the entanglement entropy after a very long time, which is, for example, 10 to the power 5 cycles. And so this is the entanglement entropy in the y-axis, and x-axis is the magnetization of your initial states. So what we observe is that even in the zero magnetization sector, there are states which have very low entanglement entropy growth, and there are, of course, states which grows a lot of have a lot of entanglement entropy. So what we identified that these low entangled states are these states. For example, the two nil states, and there are these up, up, down, down, and they're translational copies of these states. So which suggests that these nearest neighbor and the next nearest neighbor correlators, they are probably also some other emergent conservation laws. So in particular, if you take the nil state, up, down state as your initial state and evolve it with time for different system sizes, 8, 10, 12, which is exact, and then ITBD dynamics, which is for L tends to infinity, the entanglement entropy grows a little bit, and then it comes down, and it keeps on the entanglement just keeps on oscillating. And there is almost no system size dependence. Right. So To understand this, we again went back to look at the structures of your Floquet eigenstates. As before, this is the magnetization of your Floquet eigenstates. They have these separated blocks, and also the nearest and the next nearest neighbor terms, they also have this step kind of a structure, but not the, for example, the third order correlator, I mean the sigma plus 3. This correlator doesn't have this kind of a structure. So, right, and the quantity we defined delta as a function of your system sizes for these 3 emergent conservation laws, there is they remain at 0. There is no system size dependence, and for the other quantities which are not conserved, they have a strong system size dependence. And another interesting thing to note, I'm not sure whether the inset is visible. So in the inset, the x-axis is the static, the strength of the static term, which is the next nearest neighbor interaction term, and this is delta. So this shows that at 0, if the strength of your next nearest neighbor interaction term in your static Hamiltonian is 0, then delta is quite large. So the next nearest neighbor correlator is not a conserved quantity when you do not have this term in your undriven Hamiltonian. And if you put a very small next nearest neighbor interaction term in your Hamiltonian, undriven Hamiltonian, then this becomes a conservation law. So the conservation of the terms that commute with the strong field cannot be explained by simple unperturbed energy considerations, because the processes that cost much smaller unperturbed energies compared to the size of the perturbation can be prohibited by the conservation law. So the strong field prepares a bed where a weak term can produce a strong constraint over the entire spectrum in form of the conservation law. Now if we go back to, so this is the very surprising result which is done with, it's from an ongoing work with Shagnik. So we start with the up-down nil state as the initial state and look at the entanglement entropy of the final state after these number of drive cycles. So x-axis is the number of drive cycles. So this one is for a very small system, which is L equal to 4, then L equal to 8, and L equal to 12. What happens here that you started with a 0 entanglement state, and your entanglement entropy very slowly grows with time and reaches 1, and then again comes back. And the time it takes to grow the entanglement entropy from 0 to 1, it is extensive in your system size. So for a 4 size system, it's from it takes this time, and this is in 10 to the power 7 and 10 to the power 9. So the half-chain entanglement entropy shows a super oscillation, that's how we called it, with a period that scales exponentially with the system size. Yeah. So, right. So how this shows the suppression of the conservation violating processes at every order over a time scale which is exponential in L. To see that, so again, we started with this nil state, up-down state, which if you consider that these 3 are the conservation laws, so if you respect these conservation laws, then this up-down state can only mix with the partner down, up, the other nil state, but for which you need to flip L number of spins, which is extensive in system size. And now here, if you look at the overlap between these 2 states in the final wave function as a function of time, you can see that the overlap with the other, so basically the overlap, they are exchanged in time, showing that, so the throughout the process, the only two states that are involved in the dynamics are these two states and no other finite number of spin flip states that are excited during the process. So, right. So L spin flip processes, which takes exponential in the system size of time, all of the, this is the only process that occurs, and all the other processes are prohibited by the conservation laws. So to just see whether these are the only three conservation laws which can explain the entanglement entropy, the distribution of this entanglement entropy, we just calculated the page bound considering just these three conservation laws. So this just shows that there might be other conservation laws, but the page bound gives you the upper bound of the entanglement entropy that is reached by all these kind of states. So probably I was a bit quick, and so this brings me to the conclusion that dynamical freezing under strong periodic drive provides a mechanism for stabilizing interacting Floquet quantum matter via emergence of conservation laws. These emergent conservation laws are at least stable over a time scale that scales exponentially with L, and infinite size simulation shows absolutely no sign of heating for states that are constrained by the emergent conservation laws. And thank you for your attention.
Questions?
Okay, so maybe you already said, but so this emergent conservation law, it's an exact symmetry of the first order in the Magnus.
Up to the second order, all the emergent conservation laws, they commutes with the effective Hamiltonian up to the second order. Up to the second order.
And then third order?
From the third order,
it stops commuting.
No.
Huh?
It doesn't commute from the third order terms won't commute with your conservation laws, but probably I mean they are small, and that probably gives you the fluctuations around the exact magnetizations that we observe.
And they are the ones which lead to this exponential, like you're saying at exponential times.
I do not remember the exact form of the third order term. But the third order term should give you intuitively 3 spin flip processes. So for these kind of excitations where you need L spin flip processes, that will be Lth order in your Hamiltonian.
But like eventually the fact that they're not conserved, it can be seen from this third order term.
Yeah. So so if you really take the divergence of the series seriously, then everything will eventually heat up, because higher order terms are bigger, always bigger. It keeps on growing because there are factorial in processes which takes place, so everything will heat up. But the thing we see is probably there is some kind of underlying convergences which we cannot directly see from perturbation theory. Perturbation theory always gives this kind of, like you have in QED or QCD. These are all divergent theories, but you know that this divergence is not taken to be very seriously after a while. So here, we believe same thing happens, and the resonance things with Dibyendu found gives us is consistent with the fact that some convergent series is asymptotic with our divergent perturbation to the first order, because all the singularities we see in the simulations are captured by the first order singularities of the theory. There are second order singularities in the theory, third orders are there, but we do never see those things. As Anatoli told that in Fermi Pastaolam, they have this similar mystery. So the idea is you cannot take the divergence of the series higher order terms of the series very seriously. Now the question is, you have two questions. So whether this Long oscillations is a result of the higher order terms. It's not, it's just a first order term can do that in the nth order of nth order perturbation, I mean in the nth spin flip of the thing. So the idea is the conservation law does not disallow this process. Why the conservation law is there, we do not have any idea. Why these conservation laws are so stable, why they're there, this is the mystery. So, but if you assume these conservation laws are there, this is the only process which is not suppressed. And that really takes the nth order process. So what are we trying to say? There is an off-shell process and there are on-shell processes. This is the only on-shell process which is allowed by the conservation laws, and it takes an exponentially long time. And in this time, the off-shell process doesn't kick in. And in this case, we can, since the resonance can be isolated, off-shell processes are the only way to thermalize the system, and it doesn't in an exponentially long time. So that's the message.
Okay, so my question is, as you showed us, you essentially apply a very strong field and you use the field to start switching on and off.
Yeah.
And then by doing this, you kind of stabilize this emergent quasi-conservation law. Have you tried doing this also with other types of symmetries? Like, can you try and do something that's not like a U1, but another symmetry where you apply a very strong field in that direction and then maybe this stabilizes it?
Not that I tried, but my hope is it might also give you this kind of, I mean, a strong drive should give you this kind of.
Then the second question is, sometimes in these NMR experiments, they consider the spin echo type of dynamics where you apply a very strong field and then you start basically echoing out a bunch of other terms. So you stabilize effectively a quasi-conservation law. Is this mechanism similar or is it fundamentally different?
I wouldn't think it's similar because I mean it's not coming out from the it's not because you're somehow cancelling the effect of drive because of the echo out, right? Because I mean for different kind of states you can see different. I mean, for example, if you take a very random bit string state which doesn't have this kind of nearest neighbor or the next nearest neighbor correlator value quite high, they should show you a lot of dynamics. So not that they are completely frozen.
Okay.
Questions?
So when we think about freezing a quantum state, the Zeno effect comes to the mind that you do repeated measurement and you can simply freeze a state. So is there any connection or interpretation which can be associated with your freezing and the Zeno effect? So you have local conservation laws, right?
Yeah, no, global conservation laws.
Global?
Yeah.
I see.
Yeah. Okay. I mean, if you look at the individual spins, they have a lot of dynamics. They are not conserved. Only the global quantities are conserved.
So this is a state where you cannot do repeated local measurement which will freeze the state into this system into this state. This is not possible. This is what you are saying.
You can make local measurements, but the point here is
destroy the phase. So if my measurements are non-local, then it can work.
I don't know what kind of non-local basis you want to choose, but in general, first of all, this is a unitary process. Zeno effect is non-unitary. Projected to something. We are not projecting to anything. As you can see, there are states which can evolve a lot, starting, as you just mentioned, following Schrodinger dynamics over a subspace, and there is no restriction to that. Zeno means it just stays there, but it's allowed to actually explore a lot. Only respect some global conservation laws. Otherwise, it's completely free. And Zeno is just start some initial state and stay there by repeatedly projecting it very fast. So it's very different mechanism, I guess.
So Zeno cannot be a route to really freezing. Is that
Can
what
be,
you're saying?
Zeno can be a route to freezing, but it's very, very particular. You start with some particular state and you project in some basis state. And then you keep on doing it fast and it remains projected in that space. You cannot get any dynamics at all. In our freezing, you get a lot of dynamics because these restrictions are not just freezing every state. It's just respecting certain global conservation laws. You can, all the constraints respected, you can have a lot of dynamics.
Local dynamics.
Yeah, dynamics of the whole wave function.
Okay, thank you.
Are there more questions? If there are no more questions, let's thank the speaker. And